This introductory slide presents the topic case studies on remote sensing for urban resilience and explains that the session focuses on three contrasting cities: Jakarta, Cape Town and Istanbul. Each city represents a different dominant hazard: flooding and land subsidence in Jakarta, drought and water scarcity in Cape Town, and earthquakes combined with rapid urban growth in Istanbul, and illustrates how remote sensing can support ecological and risk planning under diverse conditions. Here we emphasize that, unlike previous lessons that concentrated on concepts and tools, this topic uses real-world examples to show how specific sensors, indices and workflows are applied in practice, and how their outputs feed into planning and governance decisions for disaster-resilient and sustainable cities. This class outlines the structure of the session so that students can follow the narrative. It begins with a short motivation for why case studies are useful in bridging theory and practice in urban resilience planning. The presentation then moves through three city examples: Jakarta, where remote sensing is used to monitor land subsidence and flood exposure; Cape Town, where vegetation indices support drought and water scarcity management; and Istanbul, where multi-decadal imagery documents urban expansion in a seismically active context. The session concludes with comparative insights that highlight similarities and differences in sensor choices, analysis methods and planning applications, and draws cross-cutting lessons about scalability, local limitations and stakeholder engagement. The learning objectives clarifies the expected outcomes of this case-based lesson. After completing the topic, students should be able to describe, in concrete terms, how remote sensing was employed to address resilience challenges in Jakarta, Cape Town and Istanbul, including the hazards of interest and the planning questions being answered. They should be able to identify which sensor types, such as Sentinel-1 Saudi Riyal, Sentinel-2 multispectral or Landsat time series, and which indices, such as NDVI for vegetation monitoring or other derived indicators, were used in each example. Students are expected to explain how the technical outputs, including subsidence maps, drought indicators and urban growth maps, were interpreted by planners and used to guide zoning, retrofitting or water management decisions. Finally, they should be able to reflect critically on how transferable these methods are to other cities, and what local constraints, data gaps and institutional factors may limit or enable their application. Here we motivate the use of case studies as a core part of learning in the EPD-Net module. We explain that while theoretical concepts and technical tools are essential, they only gain full meaning when seen in relation to real planning problems, institutional arrangements and local data availability. Case studies show how decisions about sensors, indices and workflows are made in practice, often under budget, time or capacity constraints. They reveal not only what is technically possible but also what is actually feasible within specific governance settings. By comparing several cities, students can see how similar remote sensing methods are adapted to contexts dominated by floods, drought or seismic risk, and they can begin to recognize patterns, for example, when SAR is preferred over optical imagery, or when vegetation indices become central to water management decisions. This comparative perspective is intended to help students think about how they might translate lessons to their own cities or regions. Here we introduce Jakarta as the first case study, focusing on its urban and hazard context. Jakarta is a rapidly growing megacity situated in a low-lying coastal and river delta environment, where extensive groundwater extraction, heavy built-up load and soft sediments have led to significant land subsidence. As subsidence lowers the land relative to sea level and river stages, flood risk from both coastal surges and riverine flooding increases, threatening large populations and critical infrastructure. Many vulnerable communities live in dense, informal or low-income neighborhoods located in floodplains or along canals, where drainage is poor and protective structures are limited. Here we set the stage for understanding why remote sensing, particularly satellite-based monitoring of ground deformation and flood patterns, has become a crucial tool for Jakarta's planners and disaster managers in assessing risk and prioritizing adaptation measures. Here we explain the key remote sensing components of the Jakarta case. We highlight that Sentinel-1 synthetic aperture radar data are used in interferometric time series analyses to measure land subsidence, sometimes down to centimeter-level vertical motion, across the city. Multi-temporal satellite imagery, both SAR and optical where clouds allow, is used to identify recurrent inundation zones and seasonal flood patterns by mapping water extent at different times of the year. These layers are combined with digital elevation models and land use or building footprint maps to understand where subsidence and flood hazard overlap with densely populated or strategically important areas. The resulting products include subsidence zoning maps and flood frequency maps that can be incorporated into risk assessments, land use plans and investment strategies for drainage, dikes and relocation programs. We focus on how remote sensing outputs are translated into planning and governance actions in Jakarta. Subsidence maps derived from Sentinel-1 time series and flood frequency maps inform land use zoning, helping authorities identify areas where new development should be restricted or where building codes need to be strengthened. These products also help prioritize investments in flood protection infrastructure, such as dikes, pumps and drainage improvements, by locating the neighborhoods where subsidence and flood hazard combine with high population exposure. In some initiatives, remote sensing information supports early warning systems and evacuation planning by showing which areas tend to flood first or most frequently during extreme events. We also note that implementation is complicated by the presence of informal settlements in high-risk zones, limited resources and fragmented institutional responsibilities, reminding students that technical tools must be embedded in broader governance reforms to be fully effective. We introduce Cape Town as the second case study, focusing on drought and water scarcity. Cape Town is a coastal city with a Mediterranean-type climate, relying on rainfall-dependent reservoirs and catchments that experienced a severe multi-year drought culminating in the widely publicized Day Zero crisis, when municipal water supplies approached critical levels. The drought exposed strong spatial inequalities in access to water and green space, with wealthier suburbs often maintaining irrigated gardens and trees, while poorer areas had limited vegetation and public parks. For resilience planning, it became essential to monitor vegetation condition, urban green spaces and water stress over time and across different neighborhoods. Remote sensing tools, especially vegetation indices derived from optical sensors, offered a way to observe these patterns consistently and to integrate them with hydrological and socio-economic information. We show details how remote sensing has been used in Cape Town to monitor vegetation and water scarcity. Time series of NDVI derived from Landsat or Sentinel-2 imagery allow analysts to track changes in vegetation greenness, which can serve as a proxy for soil moisture, irrigation practices and ecological stress across the metropolitan area. By mapping green spaces, informal settlements and peri-urban agricultural areas, INDV and related indices reveal where vegetation is declining, remaining stable or recovering during and after drought periods. These patterns are interpreted in relation to rainfall records, reservoir levels and the timing of municipal water restrictions, providing insights into how different neighborhoods respond to scarcity. Such information supports early warning, guides targeted interventions such as park investments or support for vulnerable communities, and contributes to longer-term strategies for climate-resilient green infrastructure and water-sensitive urban design. We explain how remote sensing-derived vegetation and surface indicators are used in planning decisions and debates about social justice in Cape Town. Maps of NDVI and related metrics enable planners to identify neighborhoods with limited green cover that may experience higher thermal stress and fewer recreational opportunities, which often coincide with historically marginalized communities. These insights inform decisions about where to prioritize new parks, street trees or nature-based cooling solutions. By combining remote sensing metrics with socio-economic data and community input, planners and researchers can better understand how drought and water restrictions have uneven impacts, for example where lawns and gardens are preserved in affluent areas while informal settlements have little vegetation to lose. This example highlights that remote sensing information is not neutral. It can help make inequalities visible, support claims for more equitable investment and feed into participatory planning processes that seek to balance ecological resilience with social justice. We introduce Istanbul as the third case study, emphasizing its combination of rapid urbanization and high seismic hazard. Istanbul is a densely populated megacity located near the North Anatolian Fault, with a long history of destructive earthquakes and a widely recognized probability of future large events. Over the past several decades, the city has expanded dramatically, with new housing and infrastructure extending into previously rural or peri-urban areas, some of which have unfavorable geological or topographic conditions. Remote sensing has therefore been used both to document patterns of urban growth and to relate them to seismic risk factors such as proximity to active faults, soil types and slope. We also cover post-earthquake damage assessment from the 1999 Gebze earthquake. This context makes Istanbul a key example of how multi-decadal satellite imagery and ancillary geospatial data can inform strategic decisions about retrofitting, densification and growth boundaries in a hazard-prone megacity. We describe the main remote sensing components of the Istanbul case. Landsat time series are used to perform land cover classifications over multiple dates, distinguishing built-up areas from vegetation, water and other classes. Comparing maps from different years reveals the pace and direction of urban expansion, often showing outward growth along transport corridors and into peri-urban hillsides. These urban growth maps are overlaid with geospatial layers representing fault line buffers, slope gradients, soil or ground condition information, and sometimes microzonation studies, to identify areas where rapid development has occurred in zones of elevated seismic hazard or geotechnical fragility. The resulting spatial analyses highlight high growth, high-risk corridors that may require stricter building codes, targeted retrofitting programs or reconsideration of further expansion plans, illustrating the use of remote sensing-based urban change analysis as an input to long-term seismic resilience strategies. Here we explain how remote sensing can be used to assess earthquake damage in Istanbul and similar cities. High-resolution optical satellite images acquired shortly after an event allow visual or automated detection of collapsed and heavily damaged buildings through changes in texture, shadows and roof shapes, especially when compared with pre-event imagery. Synthetic aperture radar data can be used to derive coherence change maps, in which strong drops in coherence are often associated with structural damage or debris. These methods enable the rapid generation of building or block-level damage maps that classify areas into categories such as collapsed, heavily damaged, moderately damaged or apparently unaffected. Although such analyses require careful calibration and validation, they provide crucial information during the emergency phase, supporting situational awareness when ground surveys are still incomplete and helping authorities to prioritize search and rescue, debris removal and initial relief operations. In this topic we focus on how earthquake damage maps derived from remote sensing can be used beyond the immediate emergency phase to inform recovery and long-term resilience planning in Istanbul. Once building-level damage maps are produced, they are combined in a GIS with infrastructure networks, land use data, population distribution and socio-economic indicators. This integrated view shows where severe damage coincides with high population density, critical facilities or already vulnerable communities. Planners and policymakers can use this information to prioritize which neighborhoods should receive retrofitting support, where urban renewal projects are most urgent and which locations are suitable for temporary shelters and service hubs. In some cases, repeated damage assessments from different events can highlight systematically fragile building types or areas, providing evidence for more stringent building regulations, targeted incentive programs or, where necessary, gradual relocation and land use changes. In this way, remote sensing-based damage assessment becomes part of a broader seismic resilience strategy instead of remaining a purely emergency response tool. We compare the technical approaches across Jakarta, Cape Town and Istanbul. Jakarta's risk profile, dominated by floods and land subsidence, leads to a strong reliance on Sentinel-1 Saudi Riyal interferometry for vertical ground motion monitoring and on multi-temporal SAR or optical imagery for mapping recurrent inundation. Cape Town's challenge of drought and water stress is addressed mainly through optical time series imagery and NDVI-based vegetation analysis, which track changes in green cover, irrigation and ecological stress across the urban landscape. Istanbul's combination of long-term seismic risk and rapid urbanization is studied using Landsat-based urban growth mapping and, after events, high-resolution optical and SAR data for earthquake damage assessment. Although the sensors, indices and methods differ, all three cases follow the same overarching remote sensing logic. Choose suitable sensors for the hazard and planning question. derive relevant indices or classifications, integrate them with ancillary spatial data and interpret the outputs within a clear risk and resilience framework. Here we examine how the 3 case studies illustrate different ways of translating remote sensing products into planning applications and how scalable those approaches are. In Jakarta, subsidence and flood frequency maps support zoning decisions and the prioritization of structural and non-structural flood protection measures. In Cape Town, INDV and vegetation maps inform strategies for park placement, tree planting and water-sensitive urban design, while also feeding into debates about spatial inequality. In Istanbul, urban growth and damage maps are used to highlight high-risk corridors, inform retrofitting and renewal priorities and support communication about accumulating seismic risk. Many of these methods are technically transferable because they rely on open satellite data and commonly used tools, but their successful application elsewhere depends on local resolution needs, cloud conditions, the availability of ancillary datasets and institutional capacity. We underscore that remote sensing workflows must be tailored to local governance structures, planning cultures and stakeholder processes in order to move from analytical potential to actual resilience gains. Here we highlight the limitations and local constraints that emerged across the 3 case studies. It notes that although satellite archives are extensive, some cities still face data gaps, inconsistent temporal coverage or persistent cloud cover that complicate time series analysis. Medium-resolution imagery may miss fine-grained dynamics in informal settlements or very rapidly changing peri-urban zones, requiring complementary high-resolution or UAV data that not all institutions can afford or operate. We also points out that indices, classifications and damage estimates always carry uncertainty due to sensor noise, mixed pixels, modeling assumptions and imperfect reference data, which can affect confidence in the resulting maps. Beyond technical issues, it emphasizes that political priorities, financial constraints, legal frameworks and social sensitivities may limit how strongly remote sensing evidence influences zoning, relocation, retrofitting or infrastructure investments. Recognizing these constraints is essential for realistic expectations about what remote sensing can achieve and for designing strategies that integrate it with broader governance and capacity building efforts. We offer an overall synthesis and connects the case studies back to the EPD-Net goals of ecological and disaster-resilient urban planning. It reiterates that remote sensing can play a central role in addressing very different hazards, tracking subsidence and floods in Jakarta, monitoring vegetation and water stress in Cape Town and analyzing urban growth and earthquake damage in Istanbul. In all 3 examples, the full chain from data acquisition through processing to planning applications is visible, illustrating how technical analyses are, or can be, converted into concrete decisions about zoning, infrastructure and recovery. We stress that while the methods are conceptually adaptable across cities, they require careful local calibration, validation with field data and continuous dialogue with local experts and stakeholders. We conclude by emphasizing that remote sensing evidence reaches its full potential only when embedded in inclusive planning processes that recognize social inequalities and seek to deliver resilience benefits in a fair and transparent way.